So welcome everyone. Our speaker today is Henry Klest. He obtained his PhD from Stony Brook University in 2023. And he is now working at Argonne National Lab in the Medium Energy Physics group. He's going to talk about strange new worlds.
All right, thanks for the introduction and for having me. I'm sorry for taking the liberty of changing the topic completely for what you invited me to talk about. But I'm going to talk about some of my more recent work instead of the stuff I did for my PhD. So this talk is going to focus on two kind of recent open questions in QCD. And my goal here, I know a lot of you are heavy ion people. I'm going to try to convince you that there's still some interesting stuff that we can learn about the good old protons and neutrons that are, in this table and all of us. And also to, give you a taste for some of the kind of physics for the EIC that's come around that you might not read about in the Yale report, for example. So the first question I'm going to address is how baryon number is distributed in baryons. And then I'll move to the second part of my talk, which is about what the role of strange quarks is in the mechanical structure of the proton. I'll also tell you what I mean by mechanical structure of proton. So question one, historically speaking, asking the question of how a quantum number is distributed inside a hadron has been quite a fruitful question to ask. If you asked how electric charge, okay, I realize that doesn't show up. If you asked how electric charge was distributed in protons in the 50s, you would win the Nobel Prize, also for discovering quarks. How spin is distributed in the proton quite famously kicked off this whole spin crisis that somehow the quarks aren't carrying most of the proton spin, which is very surprising. And there's been a huge, long history of experiments to study that. And then more recently, we've asked the question of how is even the mass distributed in the proton. And for a while, we didn't have a good probe for that, but we're starting to make some headway on that phenomenologically. And this has become really kind of a central goal of the physics programs of both EIC and JLab. However, there's one quantum number that the proton carries, which we really haven't talked about so far, and that is baryon number, which is a, in the low temperature standard model is a conserved quantity. Obviously, it's associated with the proton, which carries a baryon number of 1. And you can basically just trivially understand this conservation as we have no process in the kind of leading order standard model, which violates the number of net quarks. Nothing deletes a quark, basically. And the kind of obvious way then to distribute this quantum number inside the proton is to just say each of these quarks, which we know don't disappear, has a baryon number of 1/3. And you can do all of your standard model calculations, electroweak, everything with that, and that's fine. But the same is kind of true for electric charge. But that doesn't tell us anything about the distribution or dynamics of this quantum number inside the baryon. So how else could we imagine it being distributed? Funny enough, there is a prediction of this that comes from string theory, although not the string theory of nowadays, but the string theory of before QCD of the strong force. And in this model, basically where you have this confluence of QCD flux tubes at roughly the center of the baryon, this could potentially carry the baryon number, and I'll call this the baryon junction. And in the language of QCD, we would say that these strings, which you can just imagine as literally like QCD strings, are made up of very many partons, which are carrying small fractions of the proton's momentum. So they're the low X kind of gluons in the parton C. A funny anecdote. So in 1979, one of the kind of originators of this, Xavier Artrou, wrote that the string model of hadrons has a very tortuous history, which may be far from over. And this at least is one prediction that we can certainly say from this model was correct. Here we are many years later discussing the same thing. And I'll try to, also if you have any questions, please interrupt me. So I'll try to motivate why, we might say that the quarks aren't just trivially carrying the baryon number with a simple thought experiment. So let's pretend you can just pull the quarks off of a baryon. We know, if you do deep inelastic scattering, you hit one quark hard, and as you pull it off, you produce a meson, where then the original quark goes off to infinity with a antiquark produced from the string, and then they travel off to infinity as a meson. Now, if you do that, say 3 times, the thing that's left here, these quarks can be completely different flavors even, but somehow the baryon stays associated there. And so that's kind of a rough, picture of why you might think that it's not just these valence quarks, which are now, off at infinity, which are carrying the baryon number dynamically inside the proton. And this was kind of revived by Dima Kurzaev, who many of you probably know, to explain basically the large amount of baryon stopping seen at mid-rapidity in high energy collisions at that time, I guess, at the SPS. And the simple picture here is that when you have really high energies, you're pretty much not going to really stop the valence quarks. You really have a low cross section for hitting that 70 GeV quark and kicking it off to mid rapidity. And in general, at very high energies, baryons are being produced just from fragmentation. And fragmentation, of course, is just equally populating baryons and antibaryons. So it's kind of surprising that after you do these, you still, in spite of the fact that the quarks are just, the valence quarks are nominally, pretty much just traveling down the beam pipe, you still see a kind of net baryon number transport to mid rapidity, for example, at RIC. So there's kind of 2 options here. One is that for some reason or another, the actual valence quarks are stopping more than we expect them to from kind of perturbative calculations. Or the more easily stoppable gluons are carrying some, maybe small, but some portion of the baryon number of the proton. So there are some results from STAR on this, which some of you maybe know about. I won't go into too much detail on them, but basically they observe in AA, in the isobar runs, where you have the same number of nucleons, but different charges, they observe kind of different transport of charge versus baryon number, whereas, if it's the valence quarks, which are transporting to mid rapidity, you would expect the charge and baryon number would just simply track one another. There are also some results from UPCs, gamma A collisions, where they observe basically that the rapidity dependence of net baryons in that case, where you have a photon coming in and striking an ion, the rapidity dependence, so basically the angular dependence, agrees with basically what could be predicted by Reggie theory of these junctions. I would say that these are kind of hints that we're going in some interesting direction with the baryon number. I wouldn't say this is kind of a conclusive measurement so far. So how else can we experimentally learn about this? I mean, it's a difficult problem. We don't really have a clean probe of this because basically, we're doing all hard scattering stuff, and this junction is really a kind of fundamentally non-perturbative thing. You can't calculate the transfer in PQCD. You can get some idea using Reggie theory, but it's not really clear to me yet at this point whether you can really apply that in the kind of high energy inelastic regime. And so we want some kind of additional experimental handle here to help us separate these two pictures. And my idea of the smoking gun here is if we just utilize the fact that we know that at low Bjorken X in the proton, it's almost all these C gluons. So can we, in collisions where we can actually measure Bjorken X, namely electron-proton or lepton-proton scattering in general, can we look, just in this low X region and see, do we see the baryon number being transported there? And we actually have some data that we can use to do this, which is the high energy electron-proton collider HERA, which is still to this day the world's only ever electron-proton collider. The beam energies were 27.6 GeV electrons and positrons on 920 GeV protons. So in terms of rapidity away from the beam, it's actually close to the ALICE low energy 900 GeV run. This kind of allows us to probe the proton at a scale of 1 attometer, if you're generous. It ran for about 15 years, from 92 to 2007, and delivered something like 800 inverse picobarns of integrated luminosity to the two general purpose experiments, H1 and Zeus. I'm going to talk about H1, which is like the planned EIC EPIC experiment as a hermetic detector, some drift chamber and silicon tracking. The liquid argon calorimeter has very nice resolution. But most importantly, for my purposes, the data is all very well preserved and the analysis tools have been modernized. You're not digging through horrible, undocumented Fortran code like you would be if you went back to analyze some other experiments that I won't name. The idea here is we can just use the HERA data for this baryon number study. The nice thing about an EP collision is that you have only one baryon. The baryon number of the whole system is just 1. So that really reduces the complexity of the observables that you have to talk about. Also at HERA, the beam energies are high enough that the likelihood of striking a valence quark is really small. The cross-section is very much dominated by low Bjorken X. The parton distribution function of valence quarks is like 1,000 times smaller. So it's like almost a negligible fraction of what we see at HERA. So basically if we see that these baryons are being transported at low X and not at high X, that would be kind of a strong indication in favor of the junction model. So what we are trying to measure are the cross sections for lambda and anti-lambda. This is the work of Gage Tustin, who's a Stony Brook student and also Rick Shift leader. So probably some of you have heard his voice before, even if you don't know him. So the valence structure of lambda is up-down strange. So the reason we're going after lambda is that, it's a relatively high cross-section. And also we get, some additional sensitivity to the junction because we're less sensitive with lambda to the valence quarks because you have one different quark in there. But really the main reason we're going after lambda is because it has this long displaced vertex. It travels, 8 centimeters in your detector before decaying. And so that has a much, much lower background than if we tried to measure protons or something like that, which they tried to do in H1 and got it wrong, famously. So we're going after lambda. And you see here our lambda invariant mass peak, which gives us basically a background-free measurement, which is nice. So the kinematic phase space in which we're measuring, for those of you who are roughly familiar with these XQ squared diagrams, we're measuring Q squared in the range of 5 to 100, GeV squared, inelasticity Y from pretty low up to 0.6. Those can also be those kinematic cuts can be loosened because we're measuring an asymmetry of lambda and anti-lambda, so it doesn't really matter. And importantly, this orange box that we have has reach all the way down to x of 10 to the minus 4, which at Hera means we're striking partons that are carrying only like 100 MeV or so of momentum. So that's pretty low. And even a large region of this is in Bjorken X kind of lower than even what EIC, although EIC, if you go to lower Q squared, can access that same 10 to the minus 4 region, as you can see here. So this is a totally work in progress results at this point. We observe that the asymmetry is very small when we do collisions at such high energies. The results from Alice in PP at 900 GeV, so basically the same beam rapidity as we have at Hera, showed a non-zero asymmetry of about 2%, plus or minus 0.5%, which is pretty much in accordance with what we're seeing so far. Maybe ours is slightly smaller than that even. And so this is, there's this tantalizing hint that you see in this data, but we can't exactly draw any conclusions yet. But our public result should be coming soon. In the future, so presently, all we can do is ask, in longitudinal momentum space, i.e. Bjorken X, how many baryons do we have transported when we do inelastic collisions, that kind of thing. But I think one of the most exciting potential advancements of this is to actually try to look at in real space, so in radial dimension in the proton, where is the baryon number? And from that, you would expect that near the center is where most of the baryon number is living, because somehow you have the quarks kind of on the outside and the junction will be inside of them nominally. And there is actually a class of exclusive processes that has been suggested to measure this. So this is the case where you have a photon coming in, you produce a meson, but the proton ends up taking almost all of the virtual photon's momentum. So it's kind of like you struck the baryon number and launched it out. And the nice thing about an exclusive process is that you can kind of relate it to a spatial distribution. That's the kind of nice thing about exclusive processes in general. You can measure a form factor and get a spatial distribution out. And one of the interesting things is that so at Jefferson Lab in EP scattering, they see, you have a steeply falling cross-section as a function of the momentum transfer to the proton. But then when you get to the point where the proton is taking almost all of the momentum of the virtual photon, you see a huge enhancement in the cross-section, which are these points here. So the question is this telling us something? And can we just take a Fourier transform as we like to and measure some baryon radius of the proton? We need some more insight really from the theory before we can draw this conclusion. This is all kind of speculative at this point. But Zach, who many of you probably know, went through with this procedure, Fourier transforming the so-called U channel peak, and did observe something suggestively smaller than the charge radius of the proton. So this is a kind of direction for phenomenology in the future, particularly because it's very clear at this point that EIC will just totally knock this measurement out of the park. In general, I would say when you first hear about this, at least when I first heard about this, I was like, that makes no sense. I mean, the baryon number, it seems just trivially carried by the quarks. It's kind of a just fun thing to think about. And there is a kind of growing consensus, I would say, that this is actually a well-posed question and not just a tautology, which I immediately kind of thought it was just some tautological trick. But at this point, I'm getting a little bit more convinced, but we really need more experimental data. And we can make predictions that we can test with the data. And the EIC is really kind of the best tool that I see in the near future for us to study this, because we have the particle ID to study all the different flavors of baryons. We have the huge luminosity to measure small cross sections, huge rapidity acceptance to study as a function of beam rapidity, different ion species, different beam energies. It's like the best. So we're looking forward to that. Now I'll totally take us in a different direction and talk about how strange the mechanical structure of the proton is. And what the heck am I talking about? So we define the mechanical structure of the proton basically by analogy to continuum mechanics. So here is your lovely energy momentum tensor that you spent hours stressing over as a grad student or an undergrad, probably a lot of you. And we can decompose this into basically a state where we have an incoming proton, we have T mu nu, and then we have an outgoing proton state. So this is basically how does the proton interact with basically energy momentum tensor. And we decompose this into some matrix elements. So these terms in boxes are just different combinations of T mu nu, basically, T00, T11, etc. And in front of them are form factors. And these form factors actually enter cross sections for some of our experimental observables. And as I was saying before, these are Fourier transforms of spatial distribution. So through this circuitous route, we can learn about basically spatial distributions of basically mechanical forces inside the proton. So here is the very simplified, this is from Thomson's Modern Particle Physics, great book. Here is the spatial distribution, and here is the form factor. And in the case of the proton, which is what I'm going to be talking about exclusively here, you have this form factor, which this just directly enters your cross-section. And this is as a function of momentum transfer here, Q. And so you measure some cross-section that looks pretty much like that in terms of momentum transfer, and you Fourier transform that, and you get an exponential with some, basically falling behavior. And the reason, so these are canonically called the gravitational form factors. It's a bad name. Really, they should be the mechanical form factors or something like that, because we're not doing gravity here. We like to think we are, but we're not. This is only talking about the energy momentum tensor of QCD. It's not, the energy momentum tensor necessarily of gravity, although one might expect that they're relatively close to each other. But EM, EM is not contributing here. You can kind of pretend that this is what you would see if you could actually do proton graviton scattering, and that's hence the gravitational name. And one of these form factors that I'm going to be focusing on is the D term, which, interestingly enough, at zero momentum transfer, so at the at rest proton sitting there on the table, this D is actually a fundamental property of the proton in this language, in the same way that spin, charge, and mass are properties of the proton. And we have almost no information really about this D. And for that reason, it's often called basically the last global unknown property of the proton. We've measured basically everything else to a quite good precision, and D is one of the last left. And D is not just interesting because it's another thing we can measure. We can actually get stuff from the D term as well, including the distribution of pressure from QCD inside the proton. And this was a fairly famous result published in Nature, where they can literally draw the distribution of pressure, where you see at the center of the proton you have a repulsive pressure pushing you out, And then after some distance, you have a confining pressure holding you in if you're a quark. And to put this into some context, the highest pressure that we've created in the lab, as far as I know, is in diamond anvils, basically, which are used often for material science. They're something like 7 million atmospheres. The core of the sun is 250 billion atmospheres, and the ridiculous number that we get for the center of the proton is 10 to the 29 atmospheres, which is an enormous pressure, which is telling us two things. One, that the strong force is really strong. Also that the proton is small. Okay. I mean, because pressure is force per volume. So if you have a really small region, you're going to get a large pressure, even if it's not that big. But I think kind of one of the more instructive distributions is even the shear force, which we can also get directly from this D term. So this D tilde is just a Fourier transform of the D term, and then basically you just do an integral and you go to the shear force distribution in the proton if you can measure this D. And the shear force distribution, which, this doesn't have the fact that the proton is just small inside of it. The shear force distribution, something like 40 kilonewtons, which I'm told is roughly the force of like a Formula One or race car in general brake pad. And that's just, sitting there in the table inside of you, you have such great forces inside of you. So don't feel stressed at all about that fact. There's also a nice feature, which is we can even define a perhaps more instructive radius of the proton, because when you talk about the charge radius, you're basically asking just where are the quarks. But the proton isn't just quarks. That's not all we're interested in. So again, you just do an integral, and what pops out is also the mean squared mechanical radius of the proton, which has been measured on the lattice to be somewhat smaller than the charge radius of the proton, as one might naively expect. And then we can even go so far as to literally draw the force distributions in the proton, the normal force distribution and the tangential force. So I think this is cool. It's like not at all what you think we can do when we're doing QCD. So how do we do this? Again, if we could do graviton scattering, there we could actually directly measure T mu nu. But we can get around this by, if we take the second Mellon moment of the generalized parton distributions, which that's complicated. The simple fact is that if you have a massless spin-to exchange, it couples in the same way as the graviton. And in these GPDs, you have in them some portion that is basically that spin-to component. And so what this means is that, and the GPDs enter directly the cross-sections. And so in certain, kinematical regions and things like that, these gravitational form factors just fall directly into the cross-section that you measure. And our goal as experimentalists is to go, where the theory is telling us to go. And one more important point is that what I talked about in terms of the pressure and shear force and all of that is true for the total D term of the proton. There's no way to measure the total D term of the proton other than graviton scattering, but we can measure each of the individual partonic components. So the gluon D term, up quark D term, down quark D term, and then add them all up and get the total D term, which is a nice feature. And then we have different experimental processes that we can measure that access these different components, and then we can add them all up and get at the total D term. That has not been done. So far, we have only these individual parts, we haven't added them up to get the total D term yet. So when people say, oh, we've already measured the pressure distribution in the proton, that's wrong. So one of those processes is the one I discussed before. This is deeply virtual Compton scattering, where you have a photon, virtual photon coming in, real photon going out. You can draw this in terms of like the handbag diagram, where the virtual photon couples to a quark, the quark emits a photon and then goes back inside the proton. And again, this is an exclusive process. You can measure the gluon component here, Dg, with near threshold production of JXI or upsilon. So this is basically where the proton and the JXI are produced very close to each other with a relatively low relative momentum, and they interact via kind of a tower of gluons, of which there is a spin 2 exchange component involved there, is the same as DVCS. And these are that's all we have so far. There's only 2 experimental measurements, although they, for medium energy physics, have been very high profile, garnering something like 50 citations a year, which is a lot for JLab experiment, trust me. And really, the interest in this is growing, and the theory is also progressing at a very fast rate at this point. This stuff really only kicked off. People had talked about it for a long time, but this stuff only really got kicked off maybe 2018, 2019, that time. So, a lot has happened since then. What I'm going to talk about is this suggestively last term in this sum, which are the strange quarks, which, to first order, you would simply imagine that there's not that many strange quarks in the proton. So can we just neglect them? Funny enough, the answer seems to be no from the theory. So if you do this calculation in the large NC, large number of colors limit, you actually expect that this D term is the same for all parton species. So that is to say that up and down should be the same, even though nominally you have twice as many up as you do down in the proton. And this is actually borne out by lattice results, basically confirmed by results in lattice QCD. And so if we extend this argument, could it even be the case that strangeness is a similar size to up and down? And on the right here, I'm showing a model prediction, chiral quark soliton model, which predicts that up and down have a 0 momentum transfer D term of like -1, and the strange quarks are about half of that, which leads the authors of these papers to conclude that basically, if you want to get the total D term, you need to also measure this quantity.
Sorry to interrupt you.
Yes.
I guess I haven't then understood really what a D term is.
Yeah.
Is there a naive way I should
Yes. So
understand that these things are true?
yeah. So roughly speaking, it's the spatial distribution of forces. So like these components of the energy momentum tensor down here, so this D term is, so this component of, this is some components of the energy momentum tensor, some combination of these, and this is quantifying like how they're spatially distributed, basically. And then you can see, if this is a big number, then these terms are important. These terms are important in our total proton, basically. If this is a super small number, then the forces are not very large, not very important.
But then why wasn't the naive, like you said, so a proton has 2 up, like the D of the up is the most important, the D of the down is next. Like we struggled to find strangeness, it shouldn't matter. So is there some, it just falls out? Like, why should they all be the same? Like, is it?
So that is, naively, people expected exactly as you said. So this first paper, this one, that kicked off this whole thing, they only measured the up and down quarks. They didn't measure the gluons. And they said, yeah, it's just the quarks, right? But then we came along later and measured the gluons. and oh, they're actually bigger than the quarks. The effect, the D term of the gluons is actually bigger than the quarks. I mean, for now, a lot of it is just theory. So theory told us, you know, okay, maybe up and down are the same. You know, this large NC, that's just an analytic calculation you can do. Lattice also came along and numerically calculated these D terms and got these results here, where you see U and D, so that they're the green and purple here, they have basically the same D term.
But there hasn't been like a back understanding. I guess like the spin you were bringing at the
Yes.
beginning was like, well, of course, angular momentum, who'd have thought, right? But
Yeah.
sure, there's angular momentum, makes sense. And like, oh, what do you know, there is glue. It's sort of been solving the spin problem of like, once we got there, we're like, oh, crisis, and it's like, sure, what do you know, there's some angular momentum.
Yeah.
Like, there's not sort of a back idea.
I don't have a, you know, I mean, the people who did the large NC calculation would of course say, ah, yes, obviously, it's because large NC applies great, and you know, that's why up and down you know, happen to be the same.
Okay.
But yeah, I mean, I would say there's not a very good kind of understanding of intuitively why.
So it's the, trying to understand what the stress in this context means. That means there's a angular variation to the density of the.
Yeah, so there's a lot of discussion surrounding this. Because of the kind of unintuitive aspect of thinking of the proton as like a fluid almost, you know? So it's really like, if you take a certain parton species, you can imagine like, you know, a quark sitting here is feeling some force in that direction, basically. But there's a lot of contentious discussion regarding precisely how to interpret it. And even the theorists in this field give me different answers basically to your question.
I guess that you could say that, well, that's how hard it is to disturb the system in that direction. You have an external something coming in, scattering it.
Yeah.
But and these has to be correlated with some direction. Does a spin come into this or anything like that, or?
So
Momentum is some.
yeah, so like this, yeah, I mean that, you know, that one's radial, but here it's with respect to the direction of the momentum transfer,
Yeah,
basically.
okay.
That's how we get that one. Because you have to kind of look at this in this the other discussion is what, you know, Lorentz frame should you look at this stuff in? And this is, you know, very particularly in the one where, you know, you have like infinite momentum and you're looking at it just in the plane tangential to the direction of motion, basically. Yeah, I mean, the proton just sitting on the desk, you know, does not have
That's
that,
right.
because of course there's no directionality.
It does, I guess that makes sense. So think of it as it's easier to move the material within the body in for some directions versus others, I guess.
Right.
Just real quick
Yeah.
follow-up to Helen's question, the like flavor blindness of the D
Yeah.
term, does that mean we would expect like to first order in this NC limit that the proton and neutron would have roughly the same D term?
Exactly, yeah. I mean, precisely what you said, yeah. We expect that they have exactly the same D terms.
Just as I'm interpreting this more, when you separate it out by flavor and you're saying it's like the force something would experience, is it the force caused by the flavor, so like D sub U, or is it the force that flavor would experience?
It's the contribution of that flavor basically to the total force.
Like on, because I feel like the force would be different if you're.
On what is a very good question. Kind of still debated.
Okay.
I mean, it's like we can measure, you know, we can measure cross sections that tell us these things, but you know, these things, like I said, they enter cross sections, but the interpretation is still kind of lacking, in my opinion.
We have one more question on the interpretation before we go on. So, I guess, can I intuitively think of the factor of 2 for the strange contribution as, okay, the up, let's say in a proton I get 2 ups and a down, but no, I guess that doesn't make sense. Sorry. I was just trying to figure out why there would be a factor of 2 for this strain?
I think that's just a, I don't know, coincidence. I wouldn't say it's like, I wouldn't say that's a precise number. It's just in this model calculation, they got that result.
But we have that reference, does it give any kind of physical
I mean, as for why the strange gives exactly that contribution, not particularly, no. It's kind of, you do the calculation and that's what pops out. And that is also, so on the lattice, they have a pretty noisy measurement of the strange quark, which is this orange one that you can see here. But within the uncertainty, again, what we're talking about here is at 0 momentum transfer. Within the uncertainty, you could say that maybe it's half, maybe the strange quark is half the up and down, maybe it's just 0, maybe it's positive, which positive would be very, very interesting because it would tell you like there's something fundamentally different about the way that the valence quarks versus the C quarks even are contributing to the forces of the proton. So that would be a really fun result, although it's kind of not suggested by the lattice results. The lattice just suggested it's probably negative. The other thing is that a positive D term necessarily corresponds to an unstable system, which is also kind of naively what you might expect from these quarks that are just appearing out of the vacuum in the sea. So we have a lot of different predictions for this strangeness D term contribution, but how can we imagine to extract it experimentally? Basically, the only way that I think so far anyone has conceived of is to do electroproduction of phi mesons, because of course phi is nominally SS bar, and so it kind of alone, in terms of the realm of exclusive processes, couples strongly to the strangeness in the proton. However, this process has never been measured in the kinematic region that we would need to measure it to do this extraction. And that, to explain that specific kinematic region a little bit more, we need high momentum transfer. We need also near threshold. That's a very important requirement. And that requirement specifically means that the invariant mass of the final state hadrons is close to the sum of their two masses. So basically they're produced at similar momenta and they have kind of a longish time to interact with one another. And then we also want a low momentum transfer to the proton T, which is where we kind of observe the strongest sensitivity to the strangeness D term. And here is a prediction for the cross section of this process, deeply virtual phi production at a given Q squared and W. And you see the kind of nice sensitivity that you have between these different values of the strangeness D term. So if we measured this cross section, you could say pretty clearly, roughly what that value is. So me and some of my collaborators proposed an experiment to measure this using the 10.6 GeV electron beam at Jefferson Lab in Hall C. Hall C has a very interesting, from my perspective, detector setup where you have two just tiny holes basically that can analyze the momenta and direction of the particles that go there like extremely well, like 10 to the -4 momentum resolution, 100 times better than a lot of our experiments. And they can also just blast the luminosity like crazy. And since in this case, we want to measure something like a femtobarn scale cross-section, Hall C is great because they can deliver us something like 18 inverse attobarns per day on a liquid hydrogen target. So that's something like 10 million times the luminosity of Rick and something like 2,000 times high lumi LHC. And so in this experiment, we detect only a proton and an electron. And then basically from momentum and energy conservation, you can say, well, what was the mass of the state that was produced here, where you also assume that you know the proton is at rest, the incoming electron, you know the beam energy, so you can measure this so-called missing mass. And if you do that, you see this very convincing bump, which is the phi meson on top of a large kind of continuum background from DIS to pion production, all of these other processes. But our spectrometers are good enough resolution that if we fit this background, we can pull out that peak with a reasonably good precision. And we requested and received, or will receive in the future, 35 days of beam to do that. And these are our roughly estimated experimental uncertainties of something like six bins with something like 15% uncertainties, but that's pretty much good enough to give us, a kind of measurement of this at the level of kind of 0.25 in resolution, which is similar basically to the precision that was attained on the lattice with some ungodly number of core hours on NERSC. And with this, we can even draw, so the shear force, a lot of these observables, it's like you need the total D term to get it, but the shear force you can define independently for all the different parton species. And so hopefully, if our experiment works out, at the end, we'll be able to basically draw the shear force distribution for strange quarks. And I can tell you, yes, the strange quarks feel 5 kilonewtons or whatever of force on them inside the proton. And that would be fun, I think. And this experiment was approved, an A- scientific grade. And that's still good. I'm not complaining about an A-. A- is good. And we're hoping to run next fall. As you might expect, the next generation of these kinds of studies can be done at the EIC. So EPIC is a large acceptance detector, not like my measly 2 tiny pinhole spectrometers, which means we can measure the phi decay products and get rid of that horrendous background by PIDing the kaons that are produced from the decay of the phi. We'll also get, continuous kinematic coverage. Like with those 2 spectrometers, I put them in one place and I only measure, in a tiny kinematic window in Q squared, W, T, all of those variables. But can we, do the cards fall such that we can actually access this at the EIC? Because in general, these near threshold reactions are really tricky at colliders. Here is the phi meson production measurement from H1 and the same thing from Zeus. And they basically didn't go below a W of 50 GeV, which is much, much greater than the W of 2 GeV that we're trying to access at to be near threshold, quote unquote. And that you can simply understand that because the proton is almost always going, basically just down the beam pipe. It's an exclusive process. So all we have in the final state is scattered electron, phi meson, proton. And the phi and the proton have to be really close to each other for it to be near threshold. So you can see straightforwardly why at a collider, when your proton and phi are just like that, it's really tricky. The EIC, because you can go to lower beam energies where the kind of opening angle between the proton and phi kind of opens up a bit. There you can actually see the kaon decay products in the central detector in the D-rich forward region, measure the 2 kaons and reconstruct the phi, all that good stuff. We also have, quite high luminosity, at least compared to Hera at the EIC. And, like I was saying, the better far forward acceptance makes a big difference. Sadly, only the 5on41 GeV mode really lets us access this process. So the 10^100 GeV has a lot higher luminosity that it can deliver to us, but the phi is just simply too boosted. Basically, it falls directly in the the phi basically, if you go to 10 on 100 GeV, so this is for 5 on 41, and you can see here the red peak is where the kaons go, and they're, you know, nicely basically within the acceptance of the D-rich. If you go to the 10 on 100, even though you have a lot higher luminosity, that sits right basically between, in this rapidity gap between the forward and the B0. And even if they did go in the B0, you wouldn't be able to identify them as kaons. So really the 5 on 41 is the best for this. And if we take that, we say, I've run 5 on 41 for 40 weeks at the design luminosity. You can measure the cross section basically at this precision in a variety of bins in Q squared, variety of bins in W. Here I'm showing just one bin in W. But this is really the sweet spot of being near threshold, but also not too near threshold. So basically this is just to say, yes, we can do this measurement, EIC, in the 5 on 41 beam energy. So to conclude, this QCD energy momentum framework is kind of fun in that it's like a new way really of looking at hadrons. It's been, you know, kind of interesting learning about like thinking in a totally different, like the realm of continuum mechanics is totally outside of what I'm used to thinking about. And in particular, this D term gives us access to a lot of interesting quantities. And if we want that whole D term, if we want to say, you know, what is the pressure distribution of the proton like really, then we need to measure this strangeness contribution also, even if it's 0. And we have all of the nice tools for us to do this measurement in the future and really kind of take this from just some very rough measurements so far to really a kind of precision understanding of these. And I will just end and say that basically all I gave you was cliffhangers, but that means that there's a lot of exciting stuff to think about on the horizon. So thank you. Questions? Yeah, go ahead.
So this like DS where you had the like 0.25 resolution, are these different, like with this here, would I be thinking, oh, I'm trying to see if 0.25 is the correct one or 0 is the correct one, or are these just like different values that DS can take?
So these are just we have no idea basically. We have no idea what the value of this is, and these are just different predictions, assuming it's a different number.
Okay.
Just to show that, you know, just to show that this cross section has some sensitivity to this quantity. It's not like for most cross sections, you know, they're not sensitive, and so they would all just give you the same thing. And when you put those experimental uncertainties on there, you say you can't learn anything.
Okay, so what I should be getting here is not that, oh, it looks like the data is saying the number is 0. It's saying it can
Yeah.
distinguish between the different.
Exactly.
Okay.
Yeah.
This model.
Yes.
Okay. I was also wondering
Nice.
that.
Yeah, it's all projections so far. I don't have the data points. I wish I.
So you proton school, but realistically,
Mhm.
as someone who's not, say, you're doing LHC, right? You're colliding them. How, in a bigger picture, how do this give us better modeling, better theory idea for PDFs, for
So
cross sections, for
for
how do
that,
we all?
I would say this is probably useless for you, but I could say the same thing to you. What are your LHC results helping me understand better the, you know, mechanical structure of the proton, it's not, I mean, you know, like.
I shall say I'm not the guest speaker.
I mean, no, like, this is, I would say this is probably about as far from something that could impact an LHC measurement in terms of things you can actually measure about the proton structure. This is about as far
Cause
as you can get
let me
from,
take a step back. So I guess more so like, maybe not for this one, but for the
junction, of
for the
course,
junction.
yeah.
So that's more so where the question was coming from. Cause you start by the motivation. So first, I'm actually in STAR, not LAC, but just since LAC is STAR is shutting down for EIC, right? But like, I guess like, when you talk about the junction.
Yeah.
In the motivation from it came with like string theory, so I wasn't sure whether or not this ends up being a indirect proof of this. That's literally, I was just, it's more of a philosophical, I'm not putting on the spot, I just curious about it.
I mean, it would, I think, it would be evidence that the QCD string theory, which not even QCD string theory, because it's not even QCD, but like that strings are a good
Mhm.
tool for understanding the strong force. But I think we more or less kind of understand that. Like, I mean, string hadronization models are very successful. So I would say it's already a pretty good,
Mhm.
well understood. This is like, I think, you know, trying to, it's like one step further. Like you could say, yeah, strings exist, but are they really having like a meaningful impact on the quantum numbers of the proton, or are they just kind of there?
Thanks.
Yeah.
So on this plot, your asymmetry, is that the number of lambda minus the number of anti-lambda baryons? And so is that a direct correlation to the baryon number just based on like the contents of the?
Basically, yeah. I mean, you could also just see this as, so one is we see more lambda baryon than anti-baryon. And yeah, I mean, if we saw a asymmetry here, you know, that would tell us that at low York-Nex, where we expect no asymmetry whatsoever, we somehow see that those baryons are being transported over like 8 units of rapidity or something like that, which you would not expect from the valence quark picture.
But in that case, could it be that, cause I guess the idea is, you're trying to tease out for that S you need an anti-S, but couldn't it be coming from like a different, like, something, like, I don't know, like A0 short, where you could be having the anti-S, you're just not reconstructing it, or is it?
So the idea with this strangeness here is that, I mean, in the lambda, that S quark is only produced by fragmentation. So I mean, yeah, it certainly is off in some other meson that we don't measure.
Right.
But since there's no valence strangeness in the proton, we can then say that like, okay, 1/3 of the quarks in our lambda were not coming from the valence quarks of the proton.
Yeah. I guess more so, I was that constrained that the S's would only go to the lambdas is where I get the question mark. If I see the asymmetry.
Well, yeah, I mean, it doesn't,
I'm just
it doesn't.
wondering.
I mean, the S can come from anywhere in the
S
fragmentation.
goes to somewhere else instead, not just like a lambda, but that's okay.
Yeah,
I
it can.
understand the idea, I just wasn't sure whether that would, cause this one was very, actually, I don't know enough about H1 to know how you reconstructed those, so.
I mean, it's the same as anyone would reconstruct lambda, basically. And then,
If you don't mind going to the slide where you define your form factors.
yeah,
Yeah, maybe a naive question is,
So you made some mention of the charge radius.
Yeah.
Other radii, etc.
Mhm.
Does this D term have some correlation between the size of the charge radius?
So kind of explicitly, no, other than like, you kind of expect, so these terms are basically broken out such that they more or less isolate the different quantum numbers. Like, so spin is, like this B term is roughly associated with the spin. A term is like the total momentum. C bar is like the mass. So I mean, they're kind of arbitrarily constructed such that there isn't, or not arbitrarily, but intentionally constructed such that there's not that much you know, kind of convolution. So like, if the proton had a given charge radius, it doesn't necessarily mean that it has some impact on like the mechanical radius.
Second question is maybe to follow up for Risa's question. So PDF has a very similar form factor. So by measuring these E terms, etc., can you make some constraints on the PDFs which would be useful for the IC?
So the one place where the PDF enters here is, let's see. So the cross section I'm measuring does technically also depend on the PDF. So this A term, so I'm measuring a cross section that basically has this term in it. I'm trying to get at this, but this is coming directly from the PDFs. This is the integral over all x of a given parton species. So this is like the 0.0257, so the like 2.5% of the proton that is strained quarks. And for up and down, it's, you know, I don't know, 30% or whatever. The gluons are like 50%. So technically, the cross section I'm measuring does depend on the PDFs. I'm using the PDFs as an input here though, because I'm trying to, you know, get rid of this one and access this one. I mean, in principle, you could try to extract the PDFs from this, but it'd be like a.
So I see. So the claim is that for a typical process where you plug in or whatever EP, typically you don't need this extra E term, but to study this process that you're studying here, E term has a reasonable contribution for you.
Exactly, and I mean, it's like we had to look to the most obscure corner of phase space to find somewhere where this thing is actually important. So for almost everything else, it's not important. But you know, it lets us access these interesting kind of global properties. One of the interesting features of this is that the near threshold requirement is that basically C, this quantity here, is reasonably large, and D is a negative number for up, down, and gluons. So these two, and when they enter into the cross section, they actually cancel each other because A is like 0.4 or something for gluons. And so you get a big cancellation there, but strangeness has a very small A. So we get a lot of sensitivity to D, particularly in phi production.
I had a question back to the baryon junction, I think it was slide 23. You made a comment about electron proton being nice because you only have a single baryon in the initial state. I was wondering how strong your reliance on that fact is in the analysis, because I just was curious whether in-time pileup played any role. I mean, I guess it was, the luminosities aren't too high, so maybe it's not an effect at all, but I just wondered if you considered that matters.
We did not, because the event rate is something like 10 hertz.
Okay.
In spite of a, you know, 40 megahertz something bunch crossing rate. So
Okay.
that was not a consideration in this analysis. although the big tricky part is baryons coming from secondary interactions in the detector material. That's the thing that took the vast majority of the analysis, and that's also why when H1 tried to measure the proton-antiproton ratio before, they got it wrong. Because you get tons of baryons from ions hitting your detector material, but no antibaryons, basically.
Thank you.
Thanks. Any more?
I guess if I wind you back to your D.
Yep.
You talked about up quarks, down quarks, and strange quarks.
Mhm.
What about anti-up and anti-down?
They are folded into it's like, it's both. When I say up, it's both up and anti-up. And that's it's a very good question that I've asked the theorists. And it boils down to a complicated feature of the GPDs, which is that in this case, basically when you take the GPDs, you're integrating from x of -1 to 1, which includes both the quarks and antiquarks. So it is in that case both.
But does that then, I hadn't picked that up, good, but like, then, I mean, I'm just measuring C, aren't I? So the valence quarks aren't really important, is that why up, down, strange are more or less the same?
I think
So
that's,
the sum of the C.
I think that is precisely correct, but because the hadronic physics community is primarily focused on valence region, like experiments at JLab and fixed target experiments in general, I think they haven't appreciated exactly that fact in the way that, you know, higher energy people do. It's like, I think they're rediscovering that the valence quarks aren't that important when you take the proton as a whole.
And like, could you do this probe then as a function of X?
No, because you actually don't measure X in this process. You measure, and you can kind of see why, because you measure, so let's take like here. The proton comes in and then you transfer some longitudinal momentum, but then the proton stays intact. So you actually can't measure the X of the parton that initiates the reaction because you don't know how much momentum was in like this gluon versus this one. So you can only measure C, which is like in the light cone, the fraction of the proton's momentum that participated in the interaction as a whole, but you don't know X, unfortunately. And this is why there's a whole mess right now with trying to actually extract the GPDs from the experimental data, because we don't measure X. The lattice can only calculate X. And so there's like a very complicated inverse problem that the hadronic physics community is trying to solve, because we can't measure X.
This is elastic scatter.
I mean, it's technically inelastic because we're producing another thing, but you can think of it as elastic scatter. Like in this case, so for the gluon D term, you basically pretend that this photon is splitting to a CC bar and then elastically scattering off of the proton.
This thing's impressive. It's very non-perturbative, but.
Yeah, it is. Yeah, it's totally non-perturbative.
Okay, if no more questions, then let's
Thank
thank
you.
the speaker again.